Okay, good morning to all. Today we see the chemical reaction engineering 2 second unit, fluid reaction. So in the previous lectures we have seen fluid particle reaction, that is the fluid solid reaction mechanism, and what are the controlling steps. Okay, what are the relation, conversion and time, and what is the time required for complete conversion of the solid. Okay, so and what is the application in a design of the reactor, fluid solid reactor. Okay, that is the packed bed, fluidized bed type of the reactor. Now we see the fluid reaction. Okay, so rate of reaction, how to determine the rate of reaction. Okay, and its kinetics regime. Okay, there are some kinetic regimes in a fluid reaction, means where is the actually reaction occurs. Okay, and this reaction application in a tower design. Okay, so already you have studied in the mass transfer 1 absorption. Okay, in absorption you have studied the mass transfer, rate of mass transfer. Okay, so here to determine the rate of reaction. Okay, and their rate of reaction we determine by using the mass transfer rate and kinetics. Okay, rate of reaction. Okay, so this overall combination, overall rate expression will determine by the mass transfer and kinetics. Okay, so we'll say the fluid in fluid reaction, the following factors will determine the design methods used. Okay, in the design method, following three factors are very important. First one is the overall rate expression, and second one equilibrium solubility, and third one is the contacting scheme. Okay, so the overall rate expression, since material in the two separate phases must contact each other before reaction can occur, both the mass transfer and chemical rates will enter in the overall rate expression. Okay, already we discussed the mass transfer and chemical rate. Okay, these both rates will be entered in the overall rate expression. This is very important. Okay, means here in fluid reaction or there fluid particle reaction, this in heterogeneous, any type of heterogeneous type of reaction, to determine the overall rate, this mass transfer rate and chemical rate both are important. Okay, so this to determine the mass transfer rate and chemical rate, for this purpose where the reaction is actually occur in the fluid reaction. Okay, to determine, identify, and which one is the rate controlling step. Okay, this will be need to identify. Then you to determine the overall rate. Okay, then second one is the equilibrium solubility. Okay, the solubility of the reacting components, means that is the solute, will limit their movement from phase to phase. This factor will certainly influence the form of the rate equation, since it will determine whether the reaction takes place in one or both phases. Okay, means one or both phases means suppose fluid in the fluid reaction, suppose gas and liquid coming in contact, and this solute is in the entered. Okay, in a liquid phase, means from the gas phase to the liquid phase. Okay, so gas beam will be occurs, liquid beam will occur. So this solute will be diffused through the gas beam, then from the liquid beam, and then from the bulk of the liquid. Okay, means we are studied in the interface mass transfer. Okay, so this solubility means this rate is depend on the equilibrium solubility. Okay, so equilibrium solubility will be occur at the interface. The gas beam and liquid beam interface will be formed. Okay, at the interface there are some solute in the gas phase is equilibrium with the solute in the liquid phase. Okay, so it is depend on the equilibrium solubility. Okay, so the rate is depend on the equilibrium solubility. Okay, so this equilibrium solubility is important. Then the contacting scheme, this is the third one, is the contacting scheme. In the gas liquid system, semi batch and counter current contacting scheme predominate. Okay, in liquid system, mixed flow and batch contacting are used in addition to counter and co-current contacting. Okay, means in the fluid operation there is the gas liquid system. Okay, and liquid system. Okay, so this in the gas liquid system, semi batch and counter current contacting. is the scheme is the predominant. Okay, and in liquid system there is a mixed flow and batch contacting are used. Okay, mixed flow and batch contacting, in that also this counter current and co-current contacting scheme will be used, and it is a more beneficial for a rate of mass transfer. Okay, so this is the factors influence on the design of the fluid reaction. Okay, so overall rate must be important, equilibrium solubility and the contacting scheme. Okay, another factor, these are the then temperature, pressures. Okay, so these are also important. Okay, but these three are very important. Then the rate equations. Okay, so in the fluid reaction, this rate expression, overall rate expression for the reaction will have to account for the mass transfer resistance and resistance of the chemical reaction state. Okay, since the relative magnitude of these two resistance can vary greatly, we have whole spectrum of possibility, and since each situation requires its own particular analysis, our first problem is to identify this kinetic region and to select that one which matches the given physical situation. Okay, means in the interface mass transfer, when the two fluids are coming contact, then gas film and liquid film are formed. Okay, so these film interface are formed, then solute is transferred from gas film to the liquid film. Okay, means there is a mass transfer resistance will be occurred, and when means mass transfer gas film resistance and liquid film resistance are there. Okay, another third resistance will be occur, that is the mass transfer is one, second resistance will be, that is the kinetic. Okay, reaction rate resistance, then reaction resistance will be occur. Okay, in a where it is actually occur, this regime is need to identify. Okay, and it is depend on the rate of reaction between the component gas A, component of the gas, and component of the liquid. Suppose A plus B, A is the gas and B is liquid, means whether it is an instantaneous type of reaction, or it is a fast type of reaction, or intermediate type of reaction, or slow or infinite type of reaction. Okay, infinitely slow reaction. Okay, so they depend on this type of reaction. This reaction resistance will be occurs, means where it is occurs, in the gas film, it is in the liquid film is occur, or in some plane will be occur, or in the main bulk of the liquid phase it will be occur. Okay, means where it is occur, this need to identify. So this is the very important mass transfer and chemical reaction rate. Okay, this is entered in a fluid reaction, and overall rate expression be determined based on this. Okay, so this mass transfer rate and chemical reaction rate, okay, we determine, and which one is the slowest, that slowest rate, it will be the rate determining step. Okay, so this rate equation for straight mass transfer absorption, means that is the absorption case of A. Okay, so this your gas side and this is the liquid side. Okay, gas side and liquid side, this gas and liquid coming in contact, then here in the gas side, at the gas side gas film will be formed, and at the liquid side this liquid film will be formed, and here this is the interface of the gas film and liquid film. Okay, so this is the interface. Okay, this is the main body of the gas, and this is the main body of the liquid. Okay, so this PA, what is the PA? PA is the partial pressure of A, component A. A is the solute in the gas. Okay, so this PA will be partial pressure of A, and this partial pressure of A in the main body of the gas, and it is diffused through this gas film. Okay, means here why it is diffused, because there is a no concentration at the interface. Okay, so due to the concentration difference, okay, concentration gradient will be occurred, and this concentration difference means that is the partial pressure difference. Okay, so this due to this difference, okay, So this component is diffused from higher concentration to lower concentration. Okay, so it is diffused through this gas beam towards the interface of the gas liquid beam. Okay, towards the interface, and this concentration or this partial pressure of A at the interface in the gas beam is measured is the PAR is the PAR. Okay, and this A is dissolved or soluble in a liquid. This A solute is soluble in a liquid. Okay, and after this solubility, this concentration is measured. Concentration of A is measured in the liquid thing, that is the CAR. Both this PAR means this partial pressure of A in the liquid film at the interface, and concentration, this CAR is the concentration of A in the liquid film at the interface. Okay, so this at the interface, this concentration we measured, this PAR and CR, both are not equal. Okay, both are equal by using this equation, Henry's law, and both are in equilibrium. That is the PAI, which is equal to HAI into CAI. Means PI is not equal to CI, but PAI, which is equal to HAI into CI. By Henry's law, these are the equilibrium to each other. Okay, so this PI is equal to HAI into CI, assume equilibrium at the interface. HI is the constant. Okay, so this CAR means here A is entered in the liquid. There is initially there is a no A in the bulk of the liquid in this here in the bulk of the liquid. So concentration again here difference is occurred, and this A is transferred from higher concentration to lower concentration. So CAR is the means A is diffused through the liquid film. Okay, so concentration is dropped from CAI to CA, and this CA is the concentration of A in the bulk of the liquid. Okay, means already you are seeing this is the in the interface mass transfer. This is the mechanism of the interface mass transfer, and is the straight mass transfer in absorption system. Okay, in absorption column. Okay, you are studying, and this straight mass transfer will be occurred. So rate will be determined. Okay, this rate will be determined, that is the minus RA is equal to, that is the kg into PA minus PI. Okay, same way, that is the kg L okay, KL into CAI minus CA. Okay, so these are the equations of the rate of mass transfer, and this rate of mass transfer we is using here in the to determine the overall rate expression for the fluid reaction. Okay, so here gas film resistance and this liquid film resistance will be occurs. So these are the mass transfer resistance are there. Okay, so this rate equation for this, okay, so that is the minus RA, which is equal to KAG into PA minus PAR. Okay, so this KAG, that is the mass transfer coefficient of A in the gas film, or this equation, this is in mole per meter square per Pascal per second. Okay, mole, now whatever the moles are diffused, and meter square, that is the cross sectional area of the column, partial pressure per time. Okay, and this interface, if we interfacial area if we consider, and this interfacial area, then KAGA we can write in terms of interfacial area, that is mole per meter cube of contact. Okay, because A is addition, that is the interfacial area, that is the measured is the meter square per meter cube of the liquid per meter cube of the contact. So this meter square will cancel, and meter cube will be coming here. So this meter square here multiply by meter square per meter cube of contact. So this KAGA in terms of volume of the liquid, that is the mole per meter cube of contactor per Pascal per second. See, the difference is this. This is the KAG and this is KAGA. Means we are using this equation. Sometimes this mass transfer coefficient in terms of volume, means it is depend on the volume, and it is depend on the cross sectional area. Okay, so this is the difference. Okay, remember this. So this minus R is equal to Kj into Pa minus Pi in terms of this volume and in terms of cross sectional area. So for the liquid film, This is for the in the gas film, and for the liquid film, that is the minus, that is the Ra, which is equal to KL into CAI minus CA, and minus Ra is equal to KALA into CI minus CA. Similarly, this is in the mass transfer coefficient of A in the liquid film. This is the mass transfer coefficient of A in the liquid film. But this KL is depend on the cross-section area, meter square of the surface, and this KALA, it is depend on the volume of the liquid, that is the meter per meter cube of contactor. So this is the meter cube of liquid per meter square surface per second, and this meter cube of liquid per meter cube of contactor per second. So this is the rate equation, okay, for straight mass transfer. Straight mass transfer is for the absorption. In unit operation, there is an absorption unit operation. These rate equations we are already used, okay, and because this there is no reaction will be occurs, okay, only straight mass transfer will be occurred. Now, if reaction will be occurs first, okay, so in the if reaction is there, then there is a some kinetic regimes will be occurred. So these kinetic regimes is where the reaction is occurs. This is need to identify, and it is depend on the type of reaction. So we see the kinetic regime. Some cases are there for the kinetic regimes. Okay. Sometimes short notes asked on this to the explain the kinetic regimes for mass transfer and reaction in fluid reaction. So these cases you must be explained. So case A, instantaneous reaction with respect to mass transfer. Instantaneous reaction with respect to mass transfer. Consider the reaction, suppose A plus B into B to give the liquid, where A is the gas and B is the liquid. Okay, and this small b is that is the stoichiometric coefficient of the B. Okay, so similar way, previous unit we have seen the A plus B to give the product. So A is the gas and B is the solid, and small b is the that is stoichiometric coefficient. Same way, this consider the reaction instead of solid here using the liquid. Okay, so now this is the diagram sketch of this case A, instantaneous reaction with respect to mass transfer. Instantaneous reaction, very fast reaction. Okay, very fast reaction means what happened here when A in the gas phase, okay, and B of the liquid phase. Okay, when A component A is coming in contact with the B, very fast, instantaneously product will be formed. Instantaneously product will be formed. Okay, so see this, okay, this is the gas side, this is the liquid side, this is the interface, this gas film and liquid film is the form. Okay, as we know, then PA, okay, there is the partial pressure of A in the gas film, gas bulk of the gas, and is the diffused through this gas film and reach towards the interface. Okay, now A is dissolved in the liquid, so concentration of A is measured here. Okay, now this A is diffused in the liquid film. That time this B is also diffused in the, that time this B is also diffused. This is the B, concentration of B. Okay, both are reactive components. Okay, so this is the liquid is the B, and this component B is diffused through this liquid film. Diffused through this liquid from bulk of the liquid to the towards the interface. Okay, but here what happened when this A is entered in the liquid film, okay, this B is also entered in the liquid film and diffused. Okay, when A is coming in contact with the B at this plane, the product is formed. At this plane, this product is formed. Means here this is the instantaneous, very fast reaction. When A is coming in contact with the B, the product is formed. Means all A is consumed and all B is consumed. Means concentration of A and B goes drop to zero. Here, and one plane is formed. That is called, this plane is called as a reaction plane. This plane is called as a reaction plane. So this reaction plane is formed in the liquid film. Okay, so this reaction will be occurs at the reaction plane and it is in the liquid film. Okay, this is the case A, instantaneous reaction with respect to mass transfer. Okay, so this is the case A. Okay, when concentration of B is goes on increase, concentration of B is goes on increase here. Okay, means what happened? This diffusion rate of B is increases as compared to the A. So what happened? This is the B will be diffused more in the liquid film, and this plane will be moved towards the interface. Because B here concentration more as compared to A. So this A will be less, so it is, and B will be increased, so it will move towards the reaction plane. That is the case B. So this we see case A is the since an element of liquid containing either A or B but not both. The reaction will occur at a plane between A containing fluid, gas or liquid, and B containing liquid. Also, since reactant must diffuse to this reaction plane, and the rate diffusion of A and B will determine the rate, so that the change in PA or CB will move the plane way or other. This is the PA or CB, that is the concentration what we changes. Suppose case B with the instantaneous reaction, same case A is the instantaneous reaction with high CB only. Okay, means high CB already you have seen. Their reaction plane in the case A will be formed in the liquid film. So in this case, you see in the liquid film, this reaction plane when concentration of B is higher. So what happened? This concentration of B is higher, means this diffusion of B is more. So rate of mass transfer will be the more, okay, as compared to the rate of mass transfer A in the liquid film. Okay, so this whatever this concentration is the B is more, so it is more, this plane is moved towards the interface, because whatever A is, because in the liquid film there is the B is available, so when A is coming contact here with the at the interface, and when it enters in the liquid film or dissolve in the liquid film, that time coming in contact with the component B, and what happened? Product is formed. So here the concentration of A, CAR, is always 0 at the interface. Okay, this whatever A is coming here, that coming this A is coming is a contact with the liquid component B, and product is formed. So all A is consumed here at the interface. Okay, and some B, because B is more here. So all B is not a consumed, some B is there. So this B will be CBI will be formed. Concentration of B at the interface in the liquid film. Okay, so this will be the second case, that is the case B, instantaneous reaction with high CB. And this high CB means this concentration of B, if again we further increase, okay, further we increase the concentration of B, there is no effect on the reaction rate. Hence this type of reaction, suppose A plus B to give the product, that is the, in case A, this is the second order type of reaction. But in the case B, what happened? When concentration of B is increasing, and it is not effect on the rate of reaction. So what is the effect? Only concentration of the A. Okay, means this is reaction is depend on only one component, that is the A in this case. So this is the pseudo first order reaction. For this special case, the reaction plane moves to the gas liquid interface. We have seen. Hence, the overall rate will be controlled by the diffusion of A to the gas film. Only one resistance will be occur, that is the gas film resistance. Only here. This is the gas film diffusion will be. How much A is diffused? If it is the more A is diffused, rate will be increased. If less A is diffused, rate will be decreased. So it is depend on only the gas film. But in the case A, it is depend on the gas film as well as liquid film diffusion. Some of the liquid film diffusion of A and B is also. Written this. So this is the case B. Okay. So here case B, here this overall rate will be controlled by the diffusion of A to the gas film only. So rising CB further has no effect on the overall rate. Hence it is the pseudo first order type of the reaction. Okay. So this second case, case C, fast reaction, second order rate. Okay. So case A, instantaneous reaction. Case B is the instantaneous reaction, same but high CB. Now case C is the fast reaction with the second order, same reaction, A plus B to give the product. Okay, same stage will be there. But here what happened? This reaction plane is spread into the zone, and this zone in the liquid film. Okay, zone in the liquid film. So reaction zone will, because this is the fast reaction, means lower than the instantaneous reaction. When A and B come in contact with each other, then some time is required for the reaction, but it is a fast reaction. Okay, and when it is a fast reaction, means or A is spread into the liquid film, so B is also spread in the liquid film, then reaction is occurs in the liquid film. Okay, in the liquid film, and product is formed, but all A is consumed here, all A, because this is the fast reaction, so all A is consumed here, so no A will be entered in the bulk of the liquid, no A entered in the bulk of the liquid, so all A is the react to the B in the liquid film only, no A will be entered in the bulk of the liquid. So reaction will be occur in the liquid film in a zone. Okay, so this is the fast reaction. The plane of the reaction of case A spread into a zone of the reaction in which both A and B are present. The reaction is fast enough so that this reaction zones remains totally within the liquid film. No A enters the main body of the liquid to react. This is the case C. Remember case A, case B, case C. Okay, again case C, same similar way. Case D is the fast reaction with high CB. Case B, we are seeing instantaneous reaction with high CB. Similar way, case D is the fast reaction with high CB. Okay, case C is the same way. Only here increase the concentration of B. When increase the concentration of B, so this B is not a decrease. B is not a appreciably decrease in the, because high CB is there. Concentration of Bi will be very high in the at the interface. So concentration of B is high. So this reaction zone will be occurred, and A will be consumed here in the A will be consumed in the liquid film. Liquid film. Okay, this zone will be remain within the liquid film only. Okay, no A, because here high CB is available, more CB is available for reaction of the B. Okay, whatever stoichiometry requirement of the B, but it is the more CB is available, and A is the limiting component is there. So reaction rate is the, it depend on the component A only, not in the B, because when high CB is there, means there is a further increasing of the B, means it is the not affect the rate of reaction. Okay, and it is depend on only component A, means it is called as the pseudo first order type of reaction, not a second order reaction. Case C is the second order reaction, but case D is the pseudo first order reaction. Okay, so because it is depend on the only component A. Okay, so this is the CAI, and this is the CA. A is not entered in the liquid film. Okay, all A is react with the B. Okay, in a liquid film. So this is the case D. Okay, so this in this case CB does not drop appreciably within the film. CB can be taken to be constant throughout the reaction. CB is constant because it is not a drop. The second order reaction rate, case C, simplifies to more easily solve first order rate expression. Means case C is a convert into the, that is second order rate is converted into the first order rate. Hence this type of reaction is called as the pseudo first order rate of reaction. This is the case D. Now case E and F. Okay, case E and F. Okay, instantaneous reaction over, then fast reaction over. Now third case, that is the case E and F, intermediate rate. Third type is the intermediate rate of reaction. So intermediate rate with respect to mass transfer. So in this case, E is the second order type intermediate reaction, and case F is the intermediate reaction with high CB. Okay, so here explain both E and F. Hence is called as the E and F. So what is the E intermediate reaction? Saying A is diffused through this gas beam, and A is entered in the liquid. Okay, in the liquid film. And similarly, B is also diffused through this. B is also diffused through this liquid film. But here intermediate reaction. Here some time is required for the reaction. This is not a fast or instantaneous reaction. Some time is required. So some of A is reacting with the B in the liquid film. Some A is remain. Okay, that this A is entered in the liquid, in the bulk of the liquid. In the bulk of the liquid, then there some reaction will be occurred. So here what happened? The reaction will be occurs in the bulk of the liquid. Okay, bulk of the liquid. Okay, as well as in the liquid film, some small amount of this reaction will be occurs in the liquid film is also liquid film. Okay, but major reaction will be occurs in the bulk of the liquid. This is the case E. Similarly, case B, case F is the high Cb is there, instantaneous reaction high Cb. Now here this is the high and constant, Cb is not a drop appreciably, Cb is a constant. Okay, means this shown like this. This A is entered in the liquid film, and okay, and this A, some of this A is react with the B in the liquid film, but not not all A is react with the liquid, because this is the intermediate type of reaction. It is required that more time for the reaction. So this A is entered in the bulk of the liquid, and then reaction will be occur in the bulk of the liquid in this case. This is the case E and F. Okay, say in both the cases the reaction is slow enough for some A to diffuse through the film into the main body of the fluid. So conjugately A react with B in both cases within the film and the main body of the liquid. Okay, so this is case E and F. Remember this. Okay, then next slow reaction. Okay, so this fourth type is the slow reaction. Okay, case G. Case G is the slow reaction with respect to mass transfer. So here this is the liquid gas beam, this is the liquid beam, this is the bulk of the gas, this is the bulk of the liquid. Here A is diffused through the gas beam, then entered in the dissolved in a liquid. So entered in the liquid beam, this is A, CAI will be occur, and then this is the CA. Okay, this A is entered in the bulk of the liquid, but this B, CB, it is a very slow reaction, very slow reaction. We saw A and B is not a react in the liquid film, because all A is entered in the, because due to very slow reaction, this all A is entered in the bulk of the liquid, and this A is react in the with the B in the bulk of the bulk film. Okay, bulk of the liquid, bulk of the liquid, not in the liquid film. Okay, so this Cb is a constant. Cb is constant because there is a no B is react with the A. Okay, so there is a B is not a drop. Okay, so so concentration of B is a constant. So due to very slow reaction, there will be a reaction occurs in main body of the liquid. See, main body of the liquid. However, the film still provide a resistance to the mass transfer of A into the main body of the liquid. Then case H, last case is this. This is the infinitely slow reaction. Infinitely slow reaction is a very more time is required. So rate of mass transfer is and rate of mass transfer is more. Means there is a no mass transfer resistance will be occur, because there is a not consumption of the A. Only A is diffused in the gas beam and is diffused through the liquid beam. So all A will be remain constant in the bulk of the liquid and in the liquid beam. So this will be the constant. So similar way B is also constant. Similar way A is in the gas beam is also constant, because and all this there is a after because more time infinitely slow reaction, very slow reaction. So there is a more time is required for the reaction. Okay, so this is the uniform uniform composition of A and B is formed in the bulk of the liquid, in the gas beam, and in the liquid beam and bulk of the liquid. Okay, so there is a no mass transfer resistance will be occur. Only reaction will be occur in the bulk of the liquid. Okay, so rate of reaction is depend only on the reaction rate. Only overall rate will be depend on the reaction, not on the mass transfer. Okay, so in this case, the mass transfer resistance is negligible. The composition of A and B are uniform in the liquid, and the rate is determined by chemical kinetics alone, not by the mass transfer rate in the infinitely slow reaction type. So these are all are the 5 steps we have seen. Case A to H, A, B both are the that is the instantaneous reaction. Then case C and D, that is the fast reaction. E and F, intermediate type of reaction. Case G and H is the slow and infinitely slow reaction. Okay, so these kinetic regimes we are seeing. Okay, summary, we see the summary of this. This is the reaction, these kinetic regimes. Okay, case A, B, C, D, that is the instantaneous and fast reaction. This reaction only in the film. Reaction only in the film. Okay, so these two types reaction occurs in the film only. Then another is the intermediate type of reaction, that is case E and F. Here this reaction will be occur in the film as well as in the main body of the liquid. Okay, the film and main body of the liquid for case E and F. And for case G and H, this reaction only in the main body of the liquid, main body of the liquid, not in the film. Okay, in the main body. This is the summary, and this is the kinetic regimes. This regime where is the reaction is occur. This is very important and is depend on the type of reaction. Okay, so first of all we determine the kinetic regime, and then we apply the what are the equation, because we determine next lecture we see how to determine this rate of reaction. Okay, so this overall rate we determine. Okay, and it is depend on this kinetic regime. So these are the important questions based on this, that explain the factor considering in the determination of the design method in fluid reaction. Okay, 3 steps are very important. That is the overall rate expression, then second solubility, and third is the contacting scheme. Okay, then temperature. Okay, so then question 2, draw and explain the kinetic regimes in fluid reaction with respect to mass transfer. So all the cases A to H you must be explained with the sketches. Okay, draw the sketch of case A, B, C, D, E, F, G, H, and all these explanation you must be do. Okay, so this is the important questions asked. Okay, so this is the fluid type of the reaction. So any